Welcome to Unit 1, Function Analysis. And in this video, we are going to look at graphical transformations. So, we've really been spending a lot of time this unit really talking about functions and all the different properties of functions and how functions behave. And it's important that you understand how functions can be transformed. So now that we know the basic functions that we talked about previously to this, we need to explore how those basic functions can be transformed. So remember the basic, we call them parent functions, like x squared, the square root of x, the absolute value of x. Those are all our parent functions. And we want to know, how can those parent functions be transformed? So there are several types of transformations. Kind of to put them into two big categories, we have rigid and non-rigid transformations, which we'll talk a little bit more about later. But we will go through each of the different transformations one at a time. Some are very easy to see and understand. Others, not so much. You got to do a little bit of studying and remembering how to do it. So tougher functions will have multiple transformations all at once. And when you got multiple transformations all at once, things do get a little bit tricky. So it's best to look at them one at a time. And then at the end of the video, we'll kind of put a bunch together and see if we could follow it. All right, so the first type of transformations are vertical and horizontal translations. These are known as rigid transformations, because what we're doing here is we're keeping the shape of the graph intact. We're just sliding the entire function up, down, left, or right. So imagine that we have a function y equals f of x. So just kind of being very generic here, y equals f of x. And if we want to move that function left or right, just literally sliding it or gliding it left or right, we simply need to add or subtract a constant positive number inside of the function. I'll talk about what that means in a moment. So this is where you're just going to be a little bit tricky, and my guess you've probably seen this or maybe heard this before, but when you have a minus c inside of the function, that actually makes you go to the right. And you would think minus means left, but nope, minus means to the right. And then if you have a plus c inside of your function, that means that you are going to slide it to the left. And again, mostly you would think plus means to the right, but no, plus means to the left. So you do got to get, figured out there. You do have to remember that. Most kids, it doesn't take a whole lot of studying to figure out that, oh yeah, minus c inside a function goes right, plus c inside a function goes left. Then we have vertical translations. This is again sliding an entire graph up or an entire graph down. And this happens when we add or subtract a c value outside of the function. So if we add c, that's going up. And now that makes complete sense. Add should go up. So adding a c value outside of a function takes it up. And then a subtraction of a c value takes it down. So let me be very clear what I mean by inside or outside of a function. So let's start with a pretty easy parent function, the square root of x. So if I want to move this function to the right 5 units, I need to subtract 5 inside. So inside of the square root, I'm going to put the minus 5. Now, if the minus 5 was outside of the square root, then that would go down 5 units. That's why I'm talking about inside versus outside. Let me give you one more example here. If we are working with the parent function x squared, and I wanted you to move it to the left 2 units. Well, inside of the function, so inside of the square, you would add 2, hence moving it left 2 units. But if I have a plus 2 outside of the parent function x squared, that's going to move it up 2. So that's pretty easy to understand. The beginning of this is pretty simple. So let's take a look at 2 more examples here. And in these 2 examples, we're going to look at the parent function x cubed. And g of x is taking x cubed with a minus 1 on the outside. So minus 1 on the outside, that's going to be down 1 unit. So here's a picture of that. So in gray, we see the x cubed, the original parent function, and then we see that the whole graph got shifted down 1 unit. Very simple. All right, now h here actually has 2 transformations. It's got a plus 1 on the outside, so that is going to go up 1 unit. And we have a plus 2 on the inside. A plus 2 is actually going to go left 2 units. So here we see the original x cubed in gray, and then we could follow it. Sometimes it's best to kind of look at the origin here, 0, 0. And we're going to go left 2, up 1, or up 1, left 2. Either word doesn't matter. And we end this new function, h of x, right there, where it went up 1, left 2. So that's kind of a nice visualization of how these functions can get moved. And again, these are called rigid transformations because the whole graph is moving at a time. Okay, the shape is not changing at all. It's just moving around. All right, now here is another example with a square root. And this time I want you to tell me the new function. All right, so the parent function is, not the square root, I'm sorry. The parent function is the absolute value of x. So the red dotted line represents the absolute value of x. And what is the new blue function? Well, it looks like it simply went down 4 units. So we would say, okay, down means that it's going to be on the outside, a -4 on the outside. Easy, right? All right, so here's another absolute value of x in red. And then we clearly see that the blue function got slid left 2. So now you got to remember, okay, left 2 means that needs to happen on the inside. And I actually want a +2 to move it to the left 2 units. So again, kind of working backwards, I give you the graph, you give me the new function. Inside versus outside, plus versus minus, make sure you know all the differences. And here are 3 more graphs. And, you know, sometimes you might not know what the parent function is, right? And I mean, I hope you would, but you never know. But in this graph, maybe you don't know what the parent function is, so we could be generic, right? Being generic is no cubes, no square roots, no absolute values, just referring to it as f of x. So in A here, we see that the red function simply went down 3. So again, you would put that +3 outside of the generic function. Right here on B, we see that the function went left 2. So again, that would be on the inside. That'd be a +2 on the inside of this generic function I'm just calling f. And then here's another one where we see that it went right 3. So right would be on the inside, -3 on the inside of the function. So this function is x cubed. Hopefully you recognize that. But my point I'm trying to make is if you don't necessarily recognize exactly what the function is, it doesn't really matter if you just want to be generic, saying, okay, here's f of x, and then applying the inside or outside, the plus or the minus, to actually make the transformation happen. All right, the next type of transformations we're going to talk about are reflections across the axes. So we can reflect across the x-axis, we can reflect across the y-axis, or we can reflect across the origin, which is actually reflecting diagonally, I guess. So let's first talk about reflecting across the x-axis, right? So if I'm thinking about my axes and I'm reflecting across the x-axis, that means I'm going from up here to down here, reflecting across the x-axis. So notice that that changes your y-coordinate. In fact, the x-coordinate doesn't change at all, which is why the inside x is still x. The inside does not change at all. It's the overall function, the y value, that went from a positive to a negative or vice versa. So that's why a reflection across the x-axis is a negative on the outside of the function. So when you see a negative on the outside, like negative the square root of x, see, it's outside the function. Negative the absolute value of x. Negative x squared. These are happening outside the function, which is, again, taking you across the x-axis. So your x coordinates are not changing. It's your y values that are changing. All right, now we could also reflect across the y-axis. So that would be taking a point from, say, here, and reflecting it across the y-axis over to here. So this time, notice that the y-coordinate's not changing at all. The y-coordinate's actually staying the same. Both blue dots are up, whatever, let's say up 5. It's the x-coordinate that went from positive over here to negative over here. So that's why reflection across the y is when you change the x to being a negative. So that's a negative on the inside of the function is a reflection across the y. This is one of those things that you do have to study to memorize. Even honestly, me today, sometimes I have to walk myself through it just to remember, is it on the inside or outside? Which is that? Reflection across the x or y. Now, reflection across the origin actually takes you diagonally. So if you're up here, you're going to get reflected over to here. Okay, so it's actually doing both. It's changing the x and the y, which is why we see a negative on the x and a negative on the y. Now remember, f of x is just a fancy way of saying y. So that's why when I put a negative here, I'm putting a negative on the y. Now I do want to make a special note on reflections across the y-axis when there's also a horizontal shift, because this is where things get a little bit weird. So let's just look at this one right here. Everybody, hopefully right now, is saying, oh, left 2. I remember, plus doesn't mean right, plus means left 2. And you were exactly correct. But be very careful. If I would do this, notice how I have a horizontal translation, that's the plus 2, but I also have a negative on that x. What's happening here is that that negative is kind of causing a bit of an issue. So when you see both of these things happening at the same time, here's what I recommend doing. I'm all inside of the function, but take a moment to factor out that negative inside the function. And what you get is this, right? Negative x plus 2. So I haven't really changed it. It's still negative x plus 2. But now I can more clearly see the negative inside the function, which is a reflection across the y. And this is actually going to take me right 2. Now it says minus 2, but that's what I remember. Minus 2 means right 2. So when you have it looking like this right here, the reflection is there. You clearly see the negative in front of the x, which is a reflection across the y. Most students always get that right. But most students see the plus 2 and they jump and say, oh, that's left 2. Plus 2 means left 2. But that's happening after the reflection. So if you think about it, it got reflected and then it got shifted. But because it got reflected, it actually went the opposite direction because it got reflected first and then moved. Hopefully that makes sense if you're following me. So again, to combat this, what I recommend doing is when you see a negative inside the function, factor it out, right? Don't take it out of the function, please. I'm not putting it in front of the f. It's still inside the function, but factor it out, and then you'll see, oh, negative 2. That means right 2. So this function is going to the right 2. So it got reflected across the y-axis, and then it went right 2. So that's a very common mistake, and it's one of those issues where if I don't make this special note right now, a lot of kids will end up getting wrong. All right, let's do an example working with reflections. This is actually a pretty good one, and it's actually also a really easy one. So consider the rational function f of x below, 5x minus 9 divided by x squared plus 3. Let's find the function that would reflect it across the x-axis, and let's find the function that would reflect it across the y-axis. So imagine if I were to graph this, and I wanted to take the graph, and I wanted to reflect it across the x-axis. All right, now remember, reflecting across the x-axis puts a negative outside the function. So the function, instead of being f of x, is now negative f of x. So all I'm doing is I'm putting a negative outside of the function. And this is actually really, really easy. Okay, that's it, right? I put a negative outside the function. There it is right there, a negative outside the function. Now I just got to clean it up to get my new function. And remember, the negative needs to be put through either the top or the bottom, but not both. If you put it through both, you're actually canceling it out because a negative on top and negative on the bottom is actually a positive. Well, it's a negative, right? So what I tell most kids is put it across the top. So it becomes negative 5x plus 9 divided by x squared plus 3. You can only put that negative either on top or on the bottom. You can't put it on both. So most of the time I recommend putting it to the numerator. So again, that's it. You just put negative out front, and then you put it through the function. Easy. All right. Now let's reflect across the y-axis. And if you remember, across the y-axis is a negative inside the function. So that is looking something like this, where the negative is inside the function. So that means the x's inside the function have to be turned into negatives. Very easy to do, right? All you got to do is, put the negatives inside the function, not out in front of it. All right, now we just got to clean this up. 5 times negative x is negative 5x minus 9. Down here, this is actually pretty cool because negative x squared still becomes a positive x squared. The negative squared is still positive, and then plus 3. So notice that these final functions look somewhat similar, but they are still a little bit different. So it does make a difference in your functions if you're reflecting across the x or the y. So when you reflect across the x, you just simply throw a negative out in front. When you reflect across the y, the negatives need to go inside of the function. All right, let's now really emphasize something I kind of mentioned earlier, this whole idea of rigid versus non-rigid transformations. So everything we've done so far, horizontal shifts, vertical shifts, and reflections are known as rigid transformations because the basic shape of the graph remains unchanged. These transformations change only the position of the graph. So the graph just gets slid or moved around, but the shape of the graph does not change. Non-rigid transformations cause a distortion or a change in the original shape of the graph. We call these types of transformations stretches or shrinks, okay? So here we're actually distorting the graph. We're changing the shape of it. Now, most of the time when you read a textbook, you're going to see stretch and shrink. A stretch, I think, to pull apart, all right? Or I think to pull. If you're going to stretch something, you're going to pull it. If you shrink something, I think you're going to squeeze. Sorry, mistyping squeeze there. You're going to squeeze it. You're going to squish it, okay? So stretch, pull, shrink, squeeze. Most books don't use those terms, but I like to. I think it actually makes a little bit more sense. So let's talk about vertical stretches or vertical shrinks. So I wish you could actually see me right now. I know you're just hearing my voice. But imagine that I have my hands on top of each other. So one hand down, one hand up. And a stretch would be pulling my hands apart. So my bottom hand goes down, my top hand goes up, and I'm pulling it apart. Whereas a shrink is my hands squeezed together. So stretch, pull apart vertically. Shrink, squeeze vertically. Now, these happen when you multiply your function by a constant on the outside, Now, how do you know if it's a stretch or a shrink, a pull or a squeeze? Well, if your C value is greater than 1, 1.1, 2, 3, 5, 10, whatever, that's a vertical stretch. That's pulling your function apart vertically. If your C value is between 0 and 1, like 1/3, 1/2, 1/4, 0.67, whatever, that's going to be a shrink where your graph is squeezed together vertically. Now, you might say, well, what about negatives? Now, remember, a negative is a reflection. So if you have a -2, the negative is the reflection, and then the 2 is the greater than 1. That would be a stretch. So the reflection would happen first, and then the stretch. All right, let's take a look at a picture of this so you can actually kind of see what I'm talking about here. So here we have a parent function, the absolute value of x. So that's in gray, the absolute value of x. And when we multiply out in front by a number greater than 1, we notice that it got pulled, it got stretched, right? So the black function it's stretched out. If I, think about if I put a hand at the bottom and a hand at the top and I pulled them apart, that's what would happen. It would stretch. Whereas over here on the right-hand side, I multiplied the parent function by 1/3, which again is between 0 and 1, and that's going to be the vertical squeeze. So notice the black function, it looks like I took the gray function and squeezed it vertically, and it flattened out. And again, that's that squeeze or that shrink. It shrunk, right? It got flattened out. All right, next we're going to talk about horizontal stretches and shrinks. So it's the same kind of concept, but now we're talking horizontally. So imagine if I have my hand on my left and my hand on my right. I grab the left of a function, I grab the right side of a function. A stretch would be pulling that function apart horizontally, or a shrink would be taking my left and my right and squeezing my hands together, or squeezing the ends of the function together, squeezing it in. This is done by multiplying by a constant C inside the function. Now, kind of opposite here. So again, you got to really kind of study this. Maybe make note cards, study your notes, whatever. A horizontal stretch is when that C value is between 0 and 1. So when that C value is 0.25 or 1/2 or 1/3, that's when you're going to get that stretch. That's going to take the left side, the right side, and pull them apart. If your C value is greater than 1, 2, 4, 7, 1.1, 1.5, whatever, anything greater than 1, that's where you're going to get a horizontal shrink, which is going to take the left side and the right side of the graph and squeeze them together. Okay, let's take a look at that as well here. So I decided to pick a slightly more complicated function to begin with, just so we start to work with harder functions. So the original function we're working with is 2 minus x cubed. Now, you could write that as negative x cubed plus 2, and then you could see, okay, that's up 2, and the reflection is, and it's a reflection across the axes, right? So again, if you look at the gray is the original x cubed. It went up 2, and then it got reflected across the y-axis there. So you can kind of see. Let me kind of put in here at the dotted line. Here is the original cubic function right there. So notice it went up 2, that's the plus 2 in the back, and then it got reflected across the y-axis. So that's the gray function there. Now, notice here I'm multiplying by 2 inside the function. So if I multiply 2x inside the function, that looks like this, right? It's inside the function. And that's going to be 2 minus 8 cubed, because 2 cubed is 8, x cubed is x cubed. Okay, so that's the black graph here. And again, notice what happened, right? Since 2 is greater, that's going to be a squeeze. So think about that gray function, and then think if I put my hands on the left and right of it and I squeezed it together, because my value 2 was greater than 1, it squeezed, it got squished in. So the gray was the beginning function, and I squeezed it in. Now, on the right-hand side here, notice that once again, we're starting with the same function, 2 minus x cubed, but this time we're going to multiply 1/2 inside the function. So that's 2 times 1/2 x cubed, and that's 2 minus 1/8 x cubed. 1/2 cubed is 1/8. So because the C value is between 0 and 1, that's going to be a stretch. So notice the original function in gray, and then the new function in black is stretched out. It's almost like I pulled it apart. I pulled it horizontally. So if the number that you multiply by inside the function is between 0 and 1, that's going to stretch you, pulling you apart. If on the left-hand side here, if the number you multiply by inside the function is greater than 1, that's going to squeeze or shrink you in. All right, now I wanted to look at a really cool function here, and I really wanted to try to make sure you understand this, algebraically and graphically. So here's a function x cubed minus 16x, a little bit more of a complicated function, and I actually took the time to go into Desmos here so you could see the graph of it. So in red here on the left-hand side, I typed in x cubed minus 16x, and you see a nice, beautiful function here in red. Now, remember, what happens if I multiply the outside of it by 2? So if I multiply the outside of this function by 2, well, one very simple way of doing that is just to multiply the entire function by 2. Now, you could go ahead and distribute that, but just for the sake of purpose, we just leave it like that, 2 times the function. So remember, outside is going to affect you vertically. And because 2 is greater than 1, that's going to be a vertical stretch. So check this out here. If I click on this blue function, notice this is where I multiplied the entire function. I multiplied the outside by 2. Notice it stretched. So the red was the original function, and multiplying by 2 stretched it vertically, okay? Now, the other thing I could do is multiply the inside. So imagine if I multiplied the inside of the function by 1/4 x. Now remember, inside affects you horizontally, and because 1/4 is between 0 and 1, that's going to be a stretch. So vertically, bigger than 1 is the stretch. Horizontally, less than 1, greater than 0 is the stretch. And again, how do I do this? Well, this is just putting the 1/4 inside the function. That means the x's both get turned into 1/4 x because I'm putting it inside the function. And again, you could go ahead and cube that out and multiply, but for sake of time, I just literally typed it in exactly like that. So I'm trying to get you guys to understand the difference, right? In this blue graph that we already looked at, the 2 was multiplied by the entire function outside of it. Now we have this one here in purple that where the 1/4 x, the multiplication is inside the function. And notice the stretch. Look how big that stretch is. So the original function is there in red, and I stretched it way left and right. It took that original function and distorted it, stretching it left and right, and that's creating the horizontal stretch. Now remember, if you multiply the inside by a number greater than 1, you're going to get that shrink. So let's do that real quick. So let's multiply the inside by 3, and I got to do it to both values, and check out how much this shrinks down. Look at that. That's perfect example of seeing the horizontal squeeze or the horizontal shrink. So in red is the original function, and I squeezed it in horizontally because I multiplied the inside by a number greater than 1. So pretty cool there. I think that's a nice visualization of what's happening there. All right, so let's do a couple more practice problems here. Now we've learned all the different transformations now. I just want to really practice all of this. So consider the parent function f of x equals x squared, and we want to create a new function that applies the following transformations in order. So the first thing we want to do is shift it 2 units to the right. So if I'm thinking about a function, 2 units to the right would be a -2 inside the function. And then we want a vertical stretch by a factor of 3. So vertical stretch would be multiplying the outside of the function by 3. And then we want a vertical translation up 5 units. That's going to be up 5 on the outside of the function. Now I actually want to go ahead and apply that. So I'm going to take x squared. I'm going to put the x minus 2 inside of it, right? So that's taking the right 2 and putting it inside the function. And then I'm going to multiply the outside of that by 3. That's the vertical stretch. And then I'm going to add 5 for my vertical translation up 5. And that's it. Now, one thing I can do real quick is I can actually, multiply this out so I can see what it's going to look like when it's all said and done. So that's x squared minus 4x plus 4 plus 5. Distribute the 3. That's going to be 3x squared minus 12x plus 12 plus 5. And that's going to give me a final answer. Sorry, I ran out of room down there. 3x squared minus 12x. 12 plus 5 is 17. So there's my final function that is shifted right 2, stretched 3 vertically, and up 5. Now, what I want to do again here, this is actually pretty cool, and I really want to emphasize why this in order matters. Let's do it in the opposite order. So let's take this function, and let's first go up 5, okay? Now let's stretch it by a factor of 3. So that means I got to multiply everything on the outside by 3. And then I'm going to shift it to the right 2, which puts a -2 on the inside. So that would look like this. Now, because I did it in this different order, notice that something really important changes here. The 3 is around everything because that happened after the translation of 5. So now when I go ahead and do this, this is going to be 3 times x minus 2 squared plus 5. So I took the x minus 2, that's inside the function, added 5, but then the vertical stretch is on the outside of all of this. So that's going to be x squared minus 4x plus 4 plus 5, which is x squared minus 4x plus 9. Then distribute the 3, I get x squared minus 12x plus 27. So the point I'm trying to make overall here is that the order you follow the transformations does matter. And that is why, literally writing it out, being generic, just thinking about f of x, kind of being generic with that f of x, following them whether you go forward or backwards, and then applying it to the actual function. So it does make a slight difference in the functions, so make sure you follow the order I give you a problem in. All right, here's another good problem, 2 problems actually, where I want you to identify all of the transformations. Now, most kids don't struggle with this, but there's one little itty bitty thing. This is the note I mentioned earlier. When you inside the function, especially when you see a number in front of the x, factor that number out because then you'll see really what's happening. And if you do this, you're more likely to get the problems correct. So if I factor that negative out, I get x plus 5. And this is going to make it a little bit easier for me to see what's happening. So the first thing that's happening is I'm shifting the graph left 5. And if you would have looked originally right here, you might have said, no, -5 means right 5. But that's because of the reflection. So I'm actually going to go left 5. Then that's a reflection. Now remember, inside the function is changing the x. So when you change the x, that's a reflection across the y-axis. And that's one of those things where you do need to study. Remember, if you're putting the negative on the x, that changes you from the right side of the graph to left side, which is a reflection across the y-axis. And then I'm going to get a vertical stretch. Sorry, I can't, misspelled stretch there. I'm bad spelling. A vertical stretch by a factor of 3. And then we're going to go a shift up 2. Okay? So make sure you understand that. It's a little bit tricky, so just take your time. Same thing here. I see that 1/3. Now that 1/3 means there's going to be a horizontal stretch, but I got to make sure I apply this on the correct order. So on the inside, I'm actually going to factor out that 1/3. And hopefully you understood where that 6 came from, because I'm factoring out the 1/3. 2 divided by 1/3 is 6. And if you don't believe me, check my work. 1/3 times x is 1/3 x. 1/3 times 6 is 2. Now, this is what's going to make me easy to see. This actually goes to the left 6. And most kids would have never have saw that. They would have instantly said, oh, it's going to the left 2. No, because that 1/3 is in there, you got to factor it out to see that it's actually left 6. That does, and that's because of the stretch, right? It stretches. It looked like it was 2, but it stretched. And a lot of kids don't understand that. So you got to really be careful when that happens. All right, then we do see that stretch. See if I can spell it right this time. That stretch by a factor of 1/3. Again, that's going to be a horizontal stretch. Sorry, I forgot the word horizontal. Then we see a vertical stretch by a factor of 2. Then we see a negative on the outside. That's a reflection across the x-axis. So there's a lot going on here. And then don't forget, finally, we see that -8. That's going to be a down 8. That's usually one nobody gets wrong. Now, listen, I chose some pretty hard ones here that have multiple transformations. Functions like these are rare. But, you know, if you see these more difficult ones with a lot going on, it makes it a little bit easier to do some simple ones. So there's definitely a lot going on this one. But you got to really understand why it's left 6, because it got stretched, right? And if you factor out that 1/3, you'll see it a lot easier. All right, one more type of problem that's going to come up in your homework possibly here is what happens when you have a point and you're transforming a single point. So imagine we have a single point x comma y on the function f of x. I'm just being very generic here. All right, now, what if we're transformed by f of x plus 2 minus 6? Okay, well, it's important to understand transformations, right? Plus 2 is left 2. Minus 6 is down 6. So the easiest way to understand this is that the x value is going to go left 2, which is minus 2. The y value is going to go down 6. So if I were to ask you, hey, how does this new point look? Well, the original point was x comma y. The new point is going to go left 2, which is taking your x value and subtracting 2, and taking your y value and going down 6. So if I said, all right, hey, what about the point 3 comma 1? If you follow the transformation, what's the new point? Well, 3 minus 2 is 1. 1 minus 6 is -5. So the new point is 1 comma -5. Okay? And again, I'm just following what we wrote right here. All right, let's do one more of these. So the new function is -x minus 7 inside the function plus 3 on the outside. Once again, maybe factor out that negative inside the function to see that it's actually going right. I take that back. It's actually going left 7. Left 7. And then it's going to go down 3. And don't forget that the x needs to be made negative. So if you have a generic point x comma y, and I ask you, what's the new point going to look like? First off, the x becomes negative. That's because of the reflection right there on the x. And then we're going left 7, so don't forget the minus 7. And again, you might have originally said, oh, minus 7 means right 7. No. You got to remember to factor out that negative, super important. So I'm actually going left 7, which is minus 7. and then the y value is going, I wrote down, oh my gosh, I'm so sorry, up 3. It's a positive, so up 3. So again, if the original point was 3, 1, I said, what's the new point? Well, plug in 3 for x. First it becomes negative, negative 3. Minus 7 is negative 10. Then plug the 1 in for y. 1 plus 3 is 4. So there's my new point, negative 10, 4. So this is a pretty easy unit, even though it's a little bit of a longer video. It's important that you understand really how, the translations horizontally, left and right, and how when there's a reflection, that kind of gets flipped. So you thought it was going left, but because of reflection, now it's going right. Or if there's a stretch, you thought it was going right 2, but it got stretched by a factor of 3, so it's actually going 6. So that's why you really, really does help to factor out when you see something inside the function, like we saw in this last problem here. And that kind of makes it a little bit easier to see, oh, plus 7. Yeah. I know that means left 7. The negative is on the x. Okay, so negative x, left 7. So hopefully that helps you guys, because that's the one place where this can be a little bit tricky. But overall, I don't think you guys will have too many difficulties with it. All right, great video. Hopefully you learned a lot. Talk to you later.